Okay, so in example 7, let's take it from the abstract of just saying that there's a force and actually do like a real world type problem, except we're going to ignore friction. So really, how realistic is that? But, we're going to get the idea. So let's find the force required to keep a 50-pound wagon from sliding down a ramp inclined at 20 degrees to the horizontal. Let's assume there is no friction, that the forces applied aren't affected by friction in this picture. Now, what's going on? We need to pay attention to this ramp. Now, I know this isn't a physics class, but these are still important ideas. There are two forces right now acting on this ramp. One of them is this vector right here. Notice this vector goes straight down. BA is what we call our gravity vector. So BA is a vector showing gravity, because gravity always pulls everything, even if you are on, this is why things roll downhill and everything. Gravity is a vertical vector going straight down. And because that wagon weighs 50 pounds, we are going straight down. We're not going down the ramp. We're going perpendicular right below us, 50 pounds straight down. Well, BC, notice BC is not quite perpendicular with the horizontal anymore. It's perpendicular with the ramp. BC, I'm talking about this guy right here. You know what? Let's do some highlighting. That might help us see all of this. BA is that one right there. Here's BA. It was green in the picture because of that. Blah, blah, blah. This may not work so good. Here's BC. Let's try a crayon instead. That might hold up better. BC. Here in green, we're going to have vector BC. This is the force. This is the vector showing my force on the ramp. This is my force pressing on the ramp. Running out of space. Now BF. They did it in red right here. BF. Notice BF is going up the ramp. This is the force needed to pull our wagon. BF is the force needed to pull our wagon. Well, what's going on? So then I made AC. Why I did AC down here at the bottom. AC is equal to BF. And why I put AC in the picture, if I have BF, is now AC is part of this triangle where we have the difference between being pulled, the weight of the wagon being pulled straight down, and the weight of the wagon pressing on my incline. That's what we're showing here. That's what we are showing there. BC, AC is the same as the vector of BF, and I'm using vector AC because that's showing us the opening of the side between being pulled straight down and being pulled onto the ramp. Now, this little triangle right here is similar to the triangle right here that we made. And I know that because I've got parallel lines. So what we have found is this angle right here where the B is the same as this angle, so we know the 20s have to be the same. But I'm not going to require you to know a bunch of that. I will give you these measurements if needed. So what we can now do is we want to find AC. Our whole goal now is to find AC, the magnitude of that vector. So the question becomes how? Well, if we redraw, let's redraw. I'm going to redraw that triangle. I've got A and C, because here's my right angle. Boom, boom, boom. We know this one is 20. We know the hypotenuse is 50, and I want to find that side. So this can just, but look, I've got a right triangle. I know an angle and an acute angle, and I know the hypotenuse, and I don't know this side. So I can flat out solve this using trigonometry. The sine of 20 degrees, I can use my trig ratios, equals the length of the opposite side over the length of the hypotenuse. So I can go ahead and get x by itself. I can say 50 times sine 20 equals x. I put that into the calculator, and I'm going to get that I'm going to need about 17 pounds of force to keep that ramp from rolling down the incline. That's what that's telling me. Boom. Not so bad. It's a lot of times just trying to understand what the whole problem is showing us. That's why I wrote it out. So if you got any questions about that, please let me know, and I will see you when I see you.